Good afternoon, good evening. My name is Deepak Shankar from Mirabilis Design, and I will be your host today for this webinar. Please be patient. We will start in approximately 1 minute because there's a few more people that are joining the session. As soon as everybody joins, we'll get started. Hello. Hello, and welcome to this edition of Mirabilis Design's technology series on power, performance, and area at the system level. Today, the topic is how to achieve 95% plus accurate power measurement during architecture exploration. I'm your host, Deepak Shankar, the founder of Mirabilis Design. And in the next 45 minutes or so, I'll be walking you through a unique and very, very successful methodology that has helped companies and organizations optimize the power consumption of their semiconductors, systems, and software. A quick introduction to Mirabilis Design. Mirabilis Design is a Silicon Valley company that is focused on optimizing and validating system specification prior to development and integration. We are a truly global company, and we have support centers across the world. VisualSim Architect is the core modeling and simulation software that is used for power, performance, and area modeling and simulation of semiconductor systems and software. The product is primarily used in semiconductors, automotive, aerospace, and defense. And the purpose is to enable your front-end electronic product development through architecture trade-offs, systems validation, functional testing, and communication. A quick introduction to VisualSim Architect. VisualSim Architect is a graphical modeling and simulation software that has a large number of system-level IPs that are fully parameterized and supports hardware, software, and networking. It is the first and only system-level modeling solution that integrates power, timing, and behavior. This is also the reason why we are able to achieve extremely accurate power numbers and power measurement, which is why I'll be spending a lot of time talking about how we enable it and what are the benefits of the approach that we take. In addition to being a fully integrated architecture modeling environment, we have open APIs and integration to requirements tools, regression simulations, and an AI-based decision environment. The software is available both as a cloud and a desktop version. The key capabilities that make this innovation possible is first and foremost the separation of behavior and architecture. So you can either change the use cases and your workloads on a pre-existing architecture, or you can take your pre-existing use cases and test scenarios and apply them to some new architectures. This environment provides dynamic simulation. It's a combination of a discrete and continuous time simulation environment, and it allows you to do a real-time evaluation of power, timing, and behavior. The parameterized libraries support multiple levels of abstraction, and they come with a full suite of statistics and generators with APIs for integrating with other environments or integrating components from other environments into this environment, VisualSim. Now, before we go into all the details and use cases, I'm going to first talk about how we enable power to be an integrated part of architecture exploration. The key aspect is looking at the system model activity. Unlike current solutions that are focused more on taking trace data or taking event information or looking at transistor level, we first look at how the use cases is going to be modeled or impacts your overall system. When you do that, you look at the impact on power, the transition time between any power management logic. And one of the neat aspects of this capability is really incorporating hardware, software, and network into the same modeling environment. Why is this important? Whether you take a semiconductor device or you take a mission, you have a variety of processing use sources, storage, memory. You also have different application software, firmware, and other types of tasks that emulate say, the arbitration algorithm or your logic or the algorithms themselves. And of course, a network, be it on a semiconductor, which can be an AXI bus or network on chip, or at the mission level, that can be a communication network talking across antennas that might be a ground station to a satellite. Now, one of the key things that Visual Sim power technology provides is integrates an end-to-end power system, right? From generation storage to looking at consumption of different IP blocks, different devices running at different clock speeds, the different data rates, different use triggers, different interrupts, and the management based on a combination of time and custom logic. The statistics are also integrated into this power technology. So there's a variety of statistics that are utilized, plus a number of interfaces to downstream implementation as well. The way that this process happens is by looking at how the models are constructed. The models are constructed where you have the functional portion and the timing and resource portion. The functional can be your FFT algorithm, or can be the schedulers, or the arbitration, or control logic. The timing is how much time it's going to be taking to run this on, say, an accelerator or a processor or an AI engine or a GPU or a DSP, plus other resources related to memories or semaphores or interrupts or watchdog timers or other types of either hardware or software entities. Now, every one of these function and timing and resource consumption has power modes associated with it. So a simple case can be an active and idle, but you can have a variety of other power modes, as I should be discussing. Using this concept is how we have built up the power environment within Visual Sim. Now, one of the things that always comes up is, hey, system level power accuracy is insufficient. I don't know all the details. I might know the process technology, but I don't know which multiplier I'm going to use, for example. Or, for example, I don't have prior data information. Everything is going to be new in this particular case. How is this going to work? The reason that it really works is because the fact that we're not just modeling a particular device, we're modeling interaction between devices, modeling interaction between IPs and the bus and the other hardware and master and slave devices. We're modeling the software, network, and hardware, and also all the use cases and workloads. That's one of the reasons why we can get this kind of accuracy. So if you look at this, on the left-hand side, you see the performance accuracy. On the right-hand side, you see the power accuracy. This is a scenario where we're using an ARM Cortex A53 within an ultra-scale Zinc SoC FPGA device. Now, before we get detailed into how the underlying technology works, how you define the different power states or define the power values, let us go and look at the different levels of power abstractions. The first and foremost is power must be evaluated at a mission level, which means you're looking at the overall project. So it can be a car that's communicating with the pavement or with the lights or traffic signals or with other vehicles. It can be the communication that's happening across all the systems. So it can be the satellite to ground station or ground station to the other systems that are connected to it, like say the the air-based communication between different aircrafts, for example. All of these require significant amount of power consumption, and they can be looked at that level. Of course, there's also the traditional power analysis, which is at the semiconductor and at the board level. So you're looking at, say, a processor. So, you got the integer unit, you got the IND cache units, you got the floating point, you have the timers. Then, of course, at the board level, you may have some custom devices. You may have the DMA components, IOs, USB interfaces, all of those. So when you look at it, you should be able to support power at all of these abstraction levels. The reason is you want to be able to carry the power information from each level of abstraction to the next level. You also want to have to be able to provide dynamic data for all the different use cases. It's not just that the user of a particular device or a user of a particular IP should not have to go to the data sheet and say, okay, I've got the information that says 200 megahertz with 8-bit data, but I might want to have the same thing running at, say, 800 megahertz with 32 bytes of data, and I want to be able to get accurate power. I don't want to just extrapolate the information from a data sheet and plug that into my model. So this is a very clear requirement that shows that the communication must start from the IP level and go all the way to the mission level to ensure accuracy, ensure testing across a wide range of use cases, and also seeing how it impacts the other elements that go to form the system, like what should be my battery size? What should be my generation capacity? What should be the cooling cost? What should be packaging? And finally, what is the overall cost of my system? In a data center, power forms a major operational expense. In a semiconductor device, the packaging increases the size, the different supply nets will cause additional cost or additional number of pins, or adding more oscillators or voltage controllers or LDOs. So again, increases the size of your semiconductor device. Now, when we look at power modeling, you're not just looking at one particular IP. Of course, you can also look at an IP level, but you want to look at the overall system. So, the overall system can have antennas, microwave, basebands. It can be made up of a variety of either a single chip or multiple chips. So you want to look at the power at all these different levels, and you want to be able to try out different traffics or different workloads that go across these things. Because if you just look at a single IP or a single device in isolation, without having the intent of what the application is, it's really hard to say what is going to be my peak voltage, what is going to be my peak wattage of my system, or what's going to be the average power over an extended period of time. Now, I'm going to take a quick break here and let you know that we do have a chat window where you can ask any number of questions. You just type in the questions, and either myself or someone along with me, the application engineers, can answer your questions. Now, let's take a semiconductor device. So we have the hardware platform, which has accelerators, the processor, the memory controllers, the system buses, all of these entities. We associate software activity. In this case, we have two scenarios. One is an MPEG scenario, and the other is a call center scenario. We're not doing the call center. We're only going to focus on the MPEG scenario. So what we have here is that, remember, I talked about the separation of the behavior and the architecture. Now, once we separated the two together, it becomes very easy for us to define the details of what's happening in the system. So, for example, I can specify what's the power for each of the devices, or what's the power for the bus, or for the L2, or for the memory, or for the hardware accelerator. Now, when I run the simulation, I know at each point in time which task is executing on which device. Why is that critical? Let's go into the next level, which is looking at the power intent. So within a particular device, you can have multiple power domains. You can have separate power managers with its own voltage and their own ground. And when you do that, you have to define the power of each individual IP or subsystem that's in your design. Now, in this particular case, as you can see, we've got 7 different devices defined here. We also have the speed and the voltage, plus we have all the different power states defined. Now, if you notice down at the bottom here, there is, of course, the VDD for the different devices, and you can see the power levels, the voltages for different devices. But at the same time, you can also see that some of these devices have complex expressions. They're not simple expressions because they have to take into consideration your static, your dynamic, your leakage power, the information when we're assembling the models. Now, some of these, like in idle state, we can even get power data from the vendor that will give you the exact power for that particular state. So we don't really need an expression. We can just put a power value. So when you define your power, 3 things. One is you define your power for all the devices. You define all the different states. You define the different voltages. And you define the different expressions associated with each and every one of those devices. Now, once we define that, we're going to run the simulation and we generate a variety of statistics. For example, here I can see the power plot, which shows me the blue points here shows me the instant power at each point in time. The red line shows me what's the average over time. Now here you can see that the hardware accelerator is not being used at all. So you can see it's got 0 power that's being consumed, or a very minimal amount of power, just the leakage. Now this one shows me my actual statistics on my application. So what is my application actually doing? So when I look at this, you can see this is my average power value. This is the latency associated with my application. So how many frames am I able to process per unit time? And lastly, it shows me the statistics. One of them is the area statistics based on the different IP components that I've instantiated on the SoC. Using this, I can actually do a power performance trade-offs. How do I do that? There are a couple of different ways I engage. First and foremost, you can see there's a lot of different power statistics that are generated out of the system. You can see for each device, I can get current, average, and the power in each state. Plus, I can actually get power as a hierarchical system, which is I can get power from lower level states being fed to the upper level state. So you can see here, this is a hierarchical component that feeds up to the upper layer. Now, you can also get transitions. Why are transitions important? The transitions are very important for a number of reasons. One is it's very important as test benches and test data for your underlying implementation. So you can see at this time, this particular device went into active state and this is the current power. Similarly, you can see over here, this one went into standby and that's the current power. This provides you information like for UPF files, the test benches for your power, all of that can be generated out of this particular block diagram or out of this particular system. Now, in addition to this, you also want to get a global view of which devices are extremely active, which devices are idle. You want to get that particular view. So for example, here you can see the master read write interface is fairly active. The system, the hardware accelerator is only active in sections. It's not active throughout the system. The ARM gets active across the whole design. It's not really in a very periodic manner, but it's it's powered at different time periods. Why is this important? This is important from your power management standpoint. For example, here I can say, during this time, bring it down to an extremely low power state. Or for example, the DRAM, I can shut down the power to the DRAM at these time periods. All of these can help me reduce the power substantially in my system. Now, we also saw the basic elements of power, which is, the voltage, the statistics regarding performance and all of those attributes. Now, in addition to that, we can also get temperature and heat. So this gives you kind of an overview of where is going to be the heat and temperature for my particular system. It provides the ability for you to provide initial data to the thermal engineers or mechanical engineers so that they can start figuring out how the cooling is going to be implemented, what kind of packaging we're going to be using, things like that. You can see the temperature can be set up for the particular SOC device or the system by utilizing all of these parameters. Now, once you've gotten all of this data, you ran the simulation, you generated the data, the next step is to consolidate all of this into an intermediate power representation. So here you can see these are all the different devices. This is the amount of time they've been in different states. So you can see some of them don't have any activity in many states. Others have activity in all the states. You can see, so these are the first four, the active, wait, idle, and standby. Now, we also see how many transitions are going between different states. So from active to idle for the ARM was 64. Active to active was 16,241, which is either that, the device that an instruction executed immediately the next instruction, which meant that it did not move to a lower state. Similarly, for wait to wait, I'm going from one state, I'm going from one wait to another wait, which is really one portion of the pipeline is waiting, another portion is active, or another portion is active, and the other one gets waited. So you can go back and forth between them. So that it captures all of those kind of details of the power activity. So it gives you how many transitions were there. Then, of course, you get the total, you get the cumulative average. Then here, it also allocates these to different power domains. What's the voltage, the gating, and also whether it's been disabled, if power gating has been enabled or disabled. Out of this block diagram, or I'm sorry, out of this particular details over here, we can actually generate the power, UPF file. So UPF is a standard format that is used by all companies for measuring and also for providing input for the RTO and also the downstream, not just RTO, but all the way down to emulators. So using that data, that intermediate representation, we can actually generate all the details associated with the power. So we generate a complete table or generate the UPF file for the particular system. Similarly, we can also generate the test benches for the particular power system as well. So we can actually generate the system Verilog code, and then we have a Python script that can generate the actual sequences that can test your power system. So not only are we doing architecture simulation where we're doing power performance trade-offs, we're also looking at ways to improve the power efficiency, adding power management, but also generating UPF files and also the test benches for your implementation. Now, so you can see it's a complete concept to development and through integration and implementation as well, both at the semiconductor IP level, but also at the system and at the mission level. Now, one of the things you want to do is be able to run regression. The reason regression is important is because you want to be able to run for a variety of scenarios, variety of use cases, traffic, workloads, applications, things like that. So one of the things you can do is you can actually bring in requirements from your external world. It could be a standard tool like DOORS or SysML, or it can be more from the like a Excel spreadsheet that one of the product managers has. So you can import those into the system. The requirements can be performance requirements, power requirements, can be behavioral requirements, can be any of those requirements. So remember, it's always a power performance trade-off that we're really looking at. Once we get those requirements, we also have information as to what are the different runs we want, what are the different scenarios. The tool automatically generates a complete sequence of iterations, a complete sequence of regressions that can then be spun off across multi-core systems. And when you do that, it comes back at the end of the simulation to tell you which scenarios passed, which scenarios failed. So that way you can use this information to figure out what is the optimal configuration. So for example, here we started at 600 megahertz, but because the requirements, we found that run number 19, which is this scenario over here, is the one that actually passed. That's the one that satisfied all the performance and power requirements. So they remember the original was 600 megahertz. Now we're at 1 gigahertz. So which meant that your power is going to be increasing. Your total power consumption has gone up, but still, you know that that is a scenario that will give you your optimal system specification. Now, once you've done all of this, once you designed your system, you got all the definitions, you got all the details, the next step is to take it and generate documentation out of the system so that you can now hand this over to the implementation team. So not only do you generate all the documentation that is scripted, you also see the block diagrams of the hardware, the behavior use cases, plus you also get all the plots. So for example, in this case, you can see what the peak power is, what's the average power. It captures all of this information in one document that can then be handed off to the implementation team to start going ahead and developing the product. So as you can see, we go through the complete process of modeling, simulation, analysis, the debugging, optimization, now documentation. Now, once you're done with that, remember we generate the UPF and the test benches, but also we have the ability to directly connect this to an FPGA board, for example, or to C++ code that might be running on the system. And you can generate different kinds of scenarios like varying the CRC files or different types of frames can be generated. All of those can be generated for doing your downstream verification. Of course, you can also connect this with your test infrastructure, can be emulators, real-time systems, any of those, and generate the waveform out of that as well. Okay. Now that we've seen the entire methodology, let's look at what is it that we want to achieve out of this particular system. There is a first case where we didn't have any information. We're building up the system from scratch, and we start adding information based on, this is the process technology. This is the, using the tech data files, trying to figure out what's the power for each component. There are always scenarios where you might already have a prior generation design, or you might be purchasing IPs or purchasing chips from third-party vendors that you're now trying to integrate into your system. Now, in these scenarios, what you get is you get a data sheet with a block diagram. So here's the data sheet that we have with the block diagram, and you get all the power-related data. So you get the the minimum, you get the max current, you get all of that information available for you. For each different power state, you get that value. You can get also idle information, standby data as well for power from the documentation that the vendor provides you. Now you take that data, in this case, it's the NXP multimedia chipset that's used in a number of infotainment systems. Take that, and you can then start incorporating that into your particular power table. So right from your manager setup to the expressions, you can incorporate for the devices or IPs or components that in your system, incorporate the power into that particular device. Or I'm sorry, into that power table. Now, once you're done with this, you actually have now something where you can evaluate power for a particular existing system or for something where you're acquiring from a third-party IP. Now, as I said, we can look at power at an IP or an SoC level, but you can also look at power at a full system. So in this case, this is a space vehicle, and you can actually see where you have all of these different subsystems here with a controller. These are all the different use cases, the tasks in each orbit. And out of this, you can generate a variety of data. So you can generate the power data. You can see here, for example, for each of the subsystems, you can see what the cumulative average, you can generate the heat data. So you can generate a variety of statistics, even at the level of emission or a space vehicle. So mission is essentially all the different orbits, and these show you for each orbit which tasks are enabled. So it shows you all of those tasks as well, along with the deadline, which is part of your requirements. Now, having looked at it from like a semiconductor IP level to a system to a full mission, let's also now look at all of the advanced capabilities available in Visual Sim for power modeling. In addition to looking at the consumption, looking at the power management, you can also start integrating other elements of the system that are related to power. Battery is one of those. So for example, you can capture, the amount of charging, the discharging, the life cycle activity. So which means you can look at consumption, look at, what happens if you have continuous charging, what happens if you have thermal shocks, heat and temperature. Now remember, this is integrated into your performance and your power model because the state changes, the power consumed where all the devices are going to be extracting power from this. So the consumption is from here, but you also have an input that is doing the continuous charging. We do support a variety of pre-existing batteries in our database. That's already there. Now, in addition to that, we also have power generators. So power generators are in two forms, time and motor based. And we have a variety of different parameters set up so that you can describe different types of power scenarios. So it can be as simple as, I've got kinetic energy from a rotating device all the way to, I've got a solar panel or a nuclear power plant. So we can support power generation for all of these. At this point, I'm going to actually go to Visual Sim and show you. So this is the Visual Sim modeling environment. We have a complete list of libraries on the left-hand side. One of the libraries, the elements happens to be the power. So you can see all of those. But we also have other types like resources or, processors. So there's a variety of components that go to form your application libraries that are available in Visual Sim. So this is your Visual Sim modeling environment. I can click on the Go button and it's going to start running the simulation. And you can see that a variety of statistics are being generated throughout the time. And these statistics are provided for almost every part of the system. So as you can see, there is a lot of power data that's available. So we zoom in, you can see, for example, what is happening to the Bluetooth, low energy Bluetooth system. So advertise to transmit, transmit to low power mode. So you can see that how it changes the power modes as it's flowing through the system. Similarly, you can also see what is the statistics for the different, say in this case, the queues or other types of systems. You can also see what is happening, through the for each of the device components that are going through the execution on the ARM processor. In this case, is the Cortex A0. You can also see the average power. You can see the instantaneous power, and of course, you can also see the latency. So you're able to see everything in a single view, the performance, the power states, the instantaneous, the average power, the performance, the statistics on latency, all of those are captured within a single module. So this forms a very important aspect of your power modeling because now not only is the power system not working in isolation, but it's working in the context of the entire SoC or the entire system. So everybody can collaborate using a single modeling environment. For example, if I go into the device here, this is the time energy. So in this case, I'm actually using a time base. So this must be, a solar panel based device. I have the battery, which again is a component out of the library right over here, as you can see. It also has turbocharging if required, provides that information. Plus it has other things like resistance, current, temperature coefficients, and things like that. And here is the scenario. So you have the use case, which is the sensors, right from the analog front end, MCU, Bluetooth, radio transceivers. All of these are incorporated into the power, which is right over here, which is the power table. So it's got all of the different devices incorporated, and you can see that it has dependencies. So you can incorporate DVFS and AVFS directly into the model. So you can see, for example, the Bluetooth has for each of the states has different power values, and you can also have different voltage values as well for each of these devices. And of course, you can also have what we call hierarchical power. So you can incorporate not just the power for the devices, but it can go right across the network as well. So you can see what's happening to the power as it flows through the entire system. Now, when we look at advanced power, we're looking at not just that you have 2 or 3 different states. You're also looking at defining multiple states. So for example, here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different states available for these different components. Now, obviously, not all of them have activity in all the states. For example, I don't see any activity for the standby state, and also the wait state does not have any activity. But different devices have different. For example, the clock has a clock on off, clock sleep, and for the 2G and 3G. The processor off also has 2G, 3G, idle, active, and other states as well. So each device has different number of states defined. Now, these are the individual expressions associated with each one of these items. So you can see we have the leakage. So that's your leakage, has the activity, and also has the dynamic power related to the clock. So you have all of it in one single definition or in one single subsystem right over here. Now, say you have a custom block that you want to define and you want to incorporate power, or you have, say, a system C or a C++ block, you want to incorporate the power there. You do have now the ability where we have functions, and I'll be talking about it in the next slide, have functions that you can incorporate directly into your particular custom block, and that can start absorbing the events, absorbing the power information, absorbing the clock information, all of that, so that it can incorporate all the statistics into the power manager or power table module. So as you can see, it combines not just power within models that are standard, but also for custom and also for third-party provided models as well. Now, power management can be defined in 2 ways. It can be scripted or textual, or it can be defined completely in a graphical mode as well. So we provide you the power intent here, so you understand really what is it that needs to be done to transition from, say, a sleep to a low power mode, or from sleep to wake up, or from sleep to advertise, or other types of modes. What is it that the transition takes? How many cycles it takes for transition, or for example, what is the change in power to move to this new state? It captures all of those information. Why is this information important? Because this information is required for your downstream implementation, for your implementation of the UPF files or test benches or your power tests and things like that as well, that is provided here. Now, this is what I was talking about, where you do have the ability to create your own custom blocks and incorporate power into those particular custom blocks. So it gives you the ability to expand beyond just using the standard components provided in Visual Sim, but also utilize custom components or create custom components with power incorporated into them. In conclusion, one of the things that Visual Sim provides is really the ability for you to do very fast system trade-offs. And the motivation or the reason that you're able to do it is because of the fact that you're substantially reducing your model construction time and being able to do more amount of analysis because you have more statistics, you have more refinement information, you have more of the regression analysis, and being able to run different types of iterations using different use cases or different workloads. As a result of that, you can do communication, which is transferring information either in terms of documentation or like UPF files or power test benches and things like that to downstream implementation teams as well. And you can do all of your refinements in a completely uh, symmetrical process, but also doing it before you start your implementation. So in your current situation, you probably are creating your test benches while you're working on your implementation. Here, those test benches can be available in advance before you actually start your implementation or implementation of those particular modules. So that way you save substantial amount of time and you reduce your project costs substantially. With this, I hope you had a good feel for how Mirabilis Design leads system design innovation in being able to achieve extremely high power measurement during the architecture exploration phase.